All right, so what I'm going to do is to tell you about something that is not related to what I talked about yesterday, actually, except that it involves plasmons still. And this has to do with arrays of plasmonic particles. A lot of this relates pretty closely to, to what was talked about in some of the talks this morning, as you will see. Okay, this is work that I've done in collaboration with Terry Odom, Rick Van Dyne, and Chad Merkin. And especially you're going to see contributions from Terry and Chad in what I'll be talking about today. Okay, so I'm first going to talk about 1- and 2-dimensional arrays. These are arrays that are going to be made using some sort of lithography method on a surface. Okay, and then we'll be talking about 3D superlattices and what it is that does. And these are going to be bottom-up methods for making those. Okay. So we start from the beginning, okay? And for us, the beginning always was to say, well, what happens, what are the optical properties of a chain of nanoparticles? Let's just make them all be spheres. Okay, this is something that we worked on a very long time ago, and the results are ones that are all familiar to the people in this audience. Okay, if you have light coming perpendicular to this chain, and you have the polarization aligned so that it is along the chain axis, then it turns out you induce dipoles in each particle in the chain, and the induced fields from those dipoles are coherently add together. In other words, the field from one dipole is aligned with the external field at the position of the next dipole. And the net effect of that is that it shifts the plasmon resonances to the red. Okay, so the dashed line is the isolated particle, silver particle, and then as you bring the particles together, you get the plasmon resonance shifting to the red. Okay, so that's all well known. And then it turns out that if you have the polarization now perpendicular to the array axis, then the dipoles are now such that the dipole fields act destructively, and so that shifts the plasmon resonances to the blue. Okay, so no surprise in any of that. All right, so something that we just did in this series of studies was to say, well, suppose that the particles were separated by the wavelength of light. Okay, what does that lead to? Okay, so it turns out that when you look at the extinction efficiency of these silver particles, then you discover that in addition to the plasmon resonance of these particles at about 400 nanometers, there's an extra peak that shows up in the spectrum that corresponds to the wavelength equal to the array spacing in the case where the array particles are in vacuum. And so no surprise. I mean, this is where you're coupling the diffractive mode associated with the array of particles with the plasmon resonance. And so it turns out that makes it so that you get this sort of sharp peak that is in which it's a hybrid mode, a hybrid between the plasmon and the photonic modes. And you can play around with this. There are various, there's always issues about how many particles are there in the array, what are the size of the particles. In order for this to, from a practical point, be an observable effect, you need to have relatively large particles, okay? I would say at least 50 nanometers in diameter, okay? And the bigger, in a sense, the better, at least up until you're up to a couple hundred. Okay, so in this case, then, this is an easily observed effect. Well, it turns out, or easily predicted effect, it turns out at the time that we wrote this paper, nobody had actually done the experiment. Okay, but over the years since then, there have been a number of groups that have reported experiments that are seeing this sort of effect. These lattice plasmons is the term that we'll use for them. And one of them is my colleague, Terry Odom. Okay, and what she does is to make not one-dimensional arrays, but two-dimensional arrays, in this case of gold particles, on a substrate, but you use index matching to make it so that the particles are acting like they're in a homogeneous environment. Okay, and then you can see these very sharp lattice plasmon resonances, and they vary with the size of the particles. They're dispersive, of course, okay, and so you can look at their dispersion properties, various things like that. So this is all, in a sense now, just kind of standard stuff. But there's many versions of this story, and here's one that we did with Merkin, okay, in which they made an array, in this case, of gold cubes on a substrate that had a gold film. So this is Macon's a version of what Macon was talking about, and so there's this gap mode, which is what she was focusing in on between the gold particle and the gold film. That doesn't have dispersion properties. But then there's this lattice mode that is associated with the fact that the distance between the particles satisfies a diffraction condition, and that is dispersive. And so then that enables one to do, experiments and do calculations in which you basically tune one mode through the other. So the non-dispersive mode is this guy right here, and it's basically just going straight up and down. On the other hand, the dispersive mode is the one that's tuning from, from left to right, and so there's an avoided crossing here, and that's telling you about the strength of the coupling then between the photonic modes and the plasmonic mode. Okay, and it's pretty strong actually. It's really quite a strong interaction that you see in this particular problem. All right, and then there's many other versions of this sort of thing. Recently, in collaborations with Terry we've been looking at these patch arrays. So you've got not just infinite arrays of these, and Terry has the ability to make arrays that are homogeneous on the centimeter length scale, but intentionally she made patch arrays like this. And it turns out when you do this, then there's two diffraction conditions that you can satisfy, both the short distance diffraction condition and also the long distance diffraction condition. And so that leads to multiple peaks in these lattice plasmons, and some of them are extremely narrow. Okay, and so that's really an interesting thing to do. All right, so now I'd like to talk a little bit about plasmon lasers, which is an application that one can imagine doing with these lattice plasmons. Okay, so of course many of you know the state of plasmon lasers. There was a paper by Naganov et al. That involved just gold particles with a silica shell, and then there were dye molecules that were put into silica shell, and they pumped this guy with light, and you see emission that's reasonably narrow. Okay, and so they decided that was a laser. Okay, and people have been arguing about it ever since. Okay, and then there's this work from Schenk's group. Okay, in which he put a rod of cadmium selenide, in this case on a silver film, and then again you can optically pump this system, and you see light being emitted from the sort of interface between the cadmium selenide particle and the silver film. And again, it's very narrow. There's actually what look like multiple lasing modes here in this case, and the intensities in this case are very consistent with what you would expect of a laser. All right, so the Terry version of this story is to go back to these arrays of particles that I was just showing you a second ago, and then put laser dyes, essentially coating the whole system with laser dyes, okay? And then again, optically pumping the system. So they made these structures out of silver and gold, which are plasmonic, and also out of titanium and TiO2, which are not plasmonic. Okay, it turns out if this is just the extinction spectrum without laser dye, and sure enough, you see these lattice plasmon modes for gold and silver, and not for the other two. Now, if you optically pump, then it turns out you see emission, but only for silver and gold, not for the other two are just showing you the luminescence of the dye. Okay, and so again, the assumption then is that you're looking at something like laser emission in this case, and they've done a number of experiments to try to sort this out. Okay, so here they just look at a dependence on pump energy, and you discover that there's a threshold for lasing. Okay, as you might imagine. Okay, and this is looking at the emission of light, so the light comes up perpendicular to the surface, to the flat surface, and this is looking at the beam of light, the divergence of which is on the order of a degree or so. And we've done modeling of these. Okay, so we did a quantum treatment for the dye molecules, a 4-level system. Of course, in the end, you have to make up the parameters, both the spontaneous and emission parameters and the energy levels and so forth. So it's a little bit of a made-up model, but that's the way this stuff works. And then you couple that to classical electrodynamics, okay, for the array structure. So this is where you're doing FTTD at the same time that you're doing the 4-level photodynamics. Okay, and so in the end, there's a number of comparisons with the experiment made. Of course, you can always compare just the extinction spectrum alone. That shows results that are consistent, and dispersion properties of the lattice plasmon are consistent. But this is showing you the calculated emission of light. Okay, so in this case, you see again the results for silver and gold, and these have this sort of threshold-like behavior, which is similar to what's seen in the experiments. Okay, and then we've also looked at where the population inversion is large. Okay, you might expect if this is really, something related to population inversion that's plasmon-driven, that it would only be close to the gold particles. In this case, this is the cylindrical particle, and this region that's lit up here is basically the population inversion within tenths of nanometers of the gold particle that is dominating the population inversion and is responsible for for most of the light that's being observed. Okay, and here we're showing just how the population inversion can get pinned when you go up above the threshold, so this flat region of here. For the molecules that are within 50 nanometers of the particles, that you see this pinning behavior, but not for the rest of the molecules. The rest of the molecules are ones where the population inversion is smaller or it isn't inverted. Okay, and then something we did very recently, and Macon was involved in this work, was to dissolve the laser dyes in various solvents that had different indices of refraction. So this allows then for tuning of this lattice plasmon over a range of, on the order of 50 nanometers or so. And so here I'm showing you the laser emission at different wavelengths, and we tried to just model that with calculations, and it all kind of connects together pretty well. Okay, so at least we have an application that can use these lattice plasmons. Presumably, they'll also be useful for sensing applications, but we haven't tried that. Okay, so now what I'd like to do is to turn over to talking about three-dimensional arrays of particles that are made by getting DNA to link the particles together. This is a technology that was developed in Chad Merkin's group. Okay, and I won't go into a lot of the dirty details on this stuff, but basically it takes gold particles, you coat them with DNA, ethylated DNA, single strand, and then you add another strand which is complementary to these guys so that you end up with double-stranded DNA. But the end of the second strand that's added, it has a little sticky end that's sticking out here, and so that enables these particles to link together with one another. And if you have a self-complementary sticky end, then it turns out that leads to highest packing fraction type stuff where it's FCC lattice. On the other hand, if you have non-self-complementary DNAs, then it turns out at least the dominant lattice structure you'll get is a BCC lattice structure. And down here I'm showing you, first of all, the small angle X-ray measurements that did that comparing theory and experiment to show that they actually produced the lattice that they expected that they would get. And then they did eventually to learn how to stabilize these lattices with silica and bring them out of solution and then do electron microscopy with them, and you can see that the lattices are what you might expect. And here you can see some of the heterogeneous population of particles that does complicate these experiments somewhat, but basically the length of the DNA is such that it can handle that. And then another sort of direction of this area has had to do with making particles in which either the gold particles were different sizes or the links of the DNA were different sizes. It's the second of these that I'm showing you right here. So this means then that you're going to produce lower symmetry crystals. But there was this question about what crystals do you get out of this technology. And what we found was that you could develop a simple analytical model that just simply looks at the overlap between the cloud of DNA that surrounds each of these particles. And whatever crystal structure would maximize that overlap is the one that would dominate the crystallography. So that led then to this phase diagram, which depends on the ratio of the diameters of the particles and then also on the density of DNA that's on the two particles. And it turns out you see in one limit, you see the cesium chloride or BCC lattice that you expected from the result that I was showing you a second ago. This result right here. But then in addition, you can also see other lattices that show up, ALB2, CO3SI, cesium-60, 60. This corresponds to different placements of the particles around one another. Okay, and it turns out that here's showing you some results from Merkin's group in which they used those ideas and more. So it turns out you can add more particles in after you've taken away, after you've made your original lattice, or in addition, sometimes you can dissolve particles after you've made your original lattice. And so the number of lattices has just gradually been added to over the years. I think Merkin says he's up to about 25 different lattice structures that they've made using this technology. Okay, so that gives you quite a few different lattices. In addition, it turns out you can make lattices in which you use anisotropic particles. And so they've done ones with rods that make these sheets of particles. They've done these triangular prisms of gold particles that make these one-dimensional lattice structures. And actually, this area is getting richer and richer. The work that's so far been published on this this is only a fraction of what I think is ultimately capable of going in this direction. We've done a little bit of work on this, so here going back to optical properties. It turns out they figured out how to take gold disks and stack them into a one-dimensional crystal. And so this is where you end up getting, if you just have isolated gold disks, then you just get a single plasmon at about 800 nanometers. But then if you stack them like this, then it turns out they blue shift with respect to one another because of the destructive interactions of the plasmonic fields. And so it turns out that leads to this blue shifted plasmon that's right here. And they've also done ones where they've alternated big disks and small disks. And so so it turns out if the particles were isolated particles, then you'd get the spectra in the blue, where there's a redder plasmon from the smaller particle, a bluer plasmon from the bigger particle. Then you stacked them together, and it turns out now they all couple together with one another, and so that splits them. If you think about plasmon hybridization, it splits the states, and but they're all still bright. Unlike the case above, where there's a dark state that's redshifted, here you get a bright state that's both redshifted and blue shifted, and you see all that in the resulting spectra. Something that you can do if you go back to these like BCC lattices, something that's of relevance in this particular thing is using effective medium approximations to describe what the optical properties are in the limit where the volume fractions of the particles are reasonably small. Okay, so we've examined that. It turns out it works really well. Okay, so in this case, here I'm just showing you what the dielectric functions are for gold lattices with volume fractions of gold between 1 and 20%. And so, as you can imagine, right close to 520 nanometers, you get something funny that happens. And in particular, the real part gets to be really large, and that leads to a redshift of the just of the overall extinction spectra of, in this case, these are just spherical aggregates of these particles, and this is what was calculated, and this was what was measured. This rising of the real part of the dielectric function can lead to that effect. It's kind of an interesting effect. But notice that the real part never goes negative in this particular version of the result. Well, it turns out that if you do silver particles, same deal, just silver lattices with various volumes of fractions, then you discover that in this case the real part actually goes negative, okay, at about 375 nanometers, or roughly speaking. Okay, so it turns out that means then that this material acts collectively as a metal, okay, in addition to having its own plasmon resonances for each particle within the material. Okay, so that's kind of an interesting effect, so it turns out if you make just an aggregate, a spherical aggregate of these particles, that leads then to two effects. One is the redshift of the plasmon peak that is associated with the non-metallic portion of the dielectric function. But in addition, there's the rise then of a second peak in the extinction spectrum that arises from the metallic portion of the dielectric function. Okay, so that's an effect that the Merkin group has tried to observe in these experiments. And in this case, all they had was polycrystalline samples, so this was not a high-quality experiment. But they did get the extinction spectra of these aggregates for various volume fractions of silver. So the theory, you can look back at the theory ago, you just imagine that's going to gradually redshift as you go to larger and larger structures or get higher volume fractions, the same effect. Okay, and that's what happens. The dominant plasmon resonance will redshift, and you see that. But in addition, the theory says there should be another resonance that would grow up that comes from this metallic region, and you can see that indeed for the highest volume fraction that we got, we're starting to see a piece of that story. All right, so now what I'd like to do is to talk a little bit about what happens when you can make superlattice crystals that have well-defined crystal habits. So unlike the polycrystalline samples I was showing you so far, it turns out they were able to make with gold structures, they were able to make these crystal habits that have rhombic dodecahedral shapes that are micron in sizes. Okay, so these can be a few microns in size, okay, and they're built out of the superlattice material. Okay, so this then leads to the opportunities to make various kinds of measurements in which you're using the micron-sized crystal as an optical cavity, okay, and then you can see the effect of the plasmon resonances of the particles inside the lattice on those optical cavity results. So we did, in this case, looking at the Fabry-Perot resonances that are formed when you bring down the incident light perpendicular to one of the crystal faces, and then there could be the light can get trapped between two different crystal faces of this crystal, and that leads to Fabry-Perot modes. If it were just a dielectric material inside of this crystal, then you just get a series of more or less equally spaced lines in the spectrum, and you see some of that here. The red here is experiment. The blues are two different versions of theory that we did for this, and you see a bunch of lines that are well defined. But it turns out right here, about 520 nanometers, all of a sudden it's like the line that should be there is gone. Okay, but what we were able to show is that basically that corresponds to what happens when you have these hybrid modes in which you're coupling together the plasmon with these Fabry-Perot modes, and it turns out there's a band gap region associated with the plasmon dispersion diagram, and so basically you expect that you would not see any Fabry-Perot modes that are in this region, and that's exactly what happens. This is for volume fraction of 1% of gold. If you go to a 10% volume fraction, then it turns out the greater extinction associated with that is such that you wipe out the Fabry-Perot modes, except way over here to the red side of the plasmon resonance. All right, so then the last topic I wanted to just mention has to do with making films of these structures have mixtures of silver and gold particles in them. So that was a technology, another version of this technology that the Merkin group perfected, in which they can use a layer by layer assembly technique to add one layer and then another layer and then another layer, okay, of these particles onto surfaces. And so in this case, if you do this with gold and with silver, you have the opportunity to make a new kind of alloy. It's an alloy in which you have an equal number, or it could be some fractional numbers of gold and silver particles, but but each particle by itself is just pure gold or pure silver. It's just the overall material that has the composition of whatever alloy that you'd like to have. Okay, so we've done that type of experiment with these films, looking at things like extinction or reflection. And then over here, I'm showing you what you get when you make an atomic type alloy. So this is an atomic alloy. This is a nanoscale alloy. The atomic alloy, of course, is where you have every particle is an alloy particle. So down here, I'm showing you, first down at the bottom, these are simulations. These are measurements of the extinction associated with these structures. And what we see is that in this case, when you have the nanoscale alloy, you get a result as you shift from pure silver to pure gold. That's just kind of like it almost has like an isosbestic point associated with it. It's like you're transitioning from one chromophore to the other chromophore, and the simulations bear that out. On the other hand, when you have the atomic scale alloy, then it turns out that then you get charge transfer. The gold is more electron withdrawing than the silver, and so even a little bit of gold in this material will make it so that the optical properties are more gold-like than silver-like. And so that's why you get this sudden transition from a silver-like spectrum to one that is more gold-like as you vary the composition of these guys. Okay, and so that's basically a different property associated with the atomic scale alloys. All right, and then we've done one other version of this experiment in which we've looked at these structures in which they're asymmetric. So in other words, you'll have a layer of silver and then a layer of gold, or you can have alternating silver, gold, things like that. So here the interest has to do with the reflectivity associated with these alloys. We've made these films so that they're a couple hundred nanometers thick, so it turns out there's still substantial transmission through these films. And then what we did is we put pure gold on one side and look at the reflectivity here, and then pure silver on the side and look at the reflectivity here. And the question is the reflectivity the same or different? So as you can imagine, there's going to be limits where you get sort of a trivial result. If I make these films really thick, then of course you're just going to get the pure silver response to the pure gold response. On the other hand, if I make them really thin, then I'm going to get the average response. Okay, so the question is there a regime sort of in between those two limits where you get something where it's different, okay, different reflectivities, but still it's not, so it's not averaged, but it's not just a pure gold or pure silver response. So here I'm showing you the results, and here the solid lines are the measurements, and the dashed lines are the calculations. Okay, and indeed, do find, this is the silver reflectivity off the silver side, and you get what actually looks like a plasmon resonance for silver. Remember, these are flat films. Okay, there's no particles here. Okay, and then there's no particles at the sort of dielectric continuum level. Here, obviously, there are particles here, and then the red result is the corresponding gold result. So here we get this asymmetric reflectivity, which is an optical property that one wants in making various kinds of optical devices. All right, so that's all I wanted to say. And we've talked about the two-dimensional arrays that have this lattice plasmon where you satisfy a Bragg condition, as well as having plasmonic properties, and that led to these lasers that I was talking about. And then we've talked about the three-dimensional arrays, where if you have a well-defined crystal habit, then you can get these Fabry-Perot modes, and there are other optical modes that you can make. Okay, and then in addition, we've talked about these films that lead to these interesting transmission and reflection properties. All right, thank you very much.